Hello and welcome to Yeba Physics on a Wednesday afternoon. My apologies for starting the stream late. It was circumstances beyond our control, and I hope that I'm still going to have some company to join in through today's tutorial. And we intend to look at problems on chapter 32, that is on inductance. And I hope that you are getting all prepared for the test next week for those doing PHYV 102. So my name is Arnold and I'll be with you this afternoon to solve a couple of questions on inductance. So I'm just going to check. I can see I've got some company on Teams. Please confirm if you can see the screen. Please confirm if you can see the screen.
Yes, I can see the screen.
All right, thank you, for confirming. So we're just going to start right away with question 8. If you missed the earlier tutorial done yesterday, please visit the Yeba Physics YouTube channel and you'll find the recording of this tutorial. Otherwise, let's start. So the first question reads, a coil has an inductance of 3 millihenry and the current in it changes from 0.2 amps to 1.5 amps in a time interval of 0.2 seconds. What is the magnitude of the average induced EMF in the coil during this interval? Okay. So first and foremost, let's write down what information we're given. We're given the inductance 3 millihenry. Current changes, so I changes from 0.2 amps to 1.50 amps in a time interval t of 0.2 seconds. 0.2 seconds. So we should remember that EMF induced in a coil is directly proportional to the rate of change of the current. Okay, so the EMF induced, you must have seen this equation from your lecture slides, that the EMF induced is directly proportional to the rate of change of the current. All right, so and from what we have here, clearly we have every quantity that we need in order to substitute and calculate there. So what we'll just do, since we're being asked for the average magnitude, so we're not worried about the negative there. The inductance 3 times 10 to the negative 3. Then the change in current, will be from 0.2 to 1.5. From 0.2, so that will be 1.5 minus 0.2 all over the change in time, which is 0.2. So you've got your negative from there, and then you can punch this and see what you get. So you can punch also to confirm over 0.2. So I get a negative 0.1, negative 0.0195 volts. So you can see that our answers have been expressed with a prefix, so that would be 0, rather. That will be 19.5 times 10 to the negative 3 volts, which is the same as 19.5 millivolts. Okay, and we do have an option for that, so we can check, see 19.5 millivolts, so that should be our answer. So this is quite straightforward. What you need is to remember your equation and also remember how to apply it appropriately. I don't think there might be any issues on that one. Let's move on to question 9. So question 9 reads, for the circuit shown, what is the rate of change in the what is the rate of change of the current in the inductor when the current in the battery is 0.50 amps? So the question is asking us to find the rate of change in current. So we want dI over dt. That is what the question is asking us to find, right? And what are we given? So I'm just going to scroll down so you can see the entire circuit. So this is how the circuit looks like. We're told that the current flowing, I, in the battery is equal to a 0.5 amps. That's the current flowing in the battery. So the question is saying find the rate of change of current in the inductor. All right. So earlier on we used the equation E equals to L di over dt. Okay, so now we need to find, for us to be able to use this equation, which means we need the voltage across, or the potential difference across the inductor, so that we can appropriately use this equation. So the voltage across the inductor would be equals to your negative L di over dt. Okay, so now what can we do now to find the voltage across the inductor? So if we get the voltage across the inductor, the inductance we already have, which means that to find di over dt would now be straightforward, right? To find di over dt will now be straightforward, which means that di dt will be equals to voltage across the inductor over the inductance, right? So this is the equation that we're going to use, provided we've first identified or determined the voltage across the inductor. So how can we find the voltage across the inductor? We're simply going to use our concept of current in a series circuit. So we can see that we have got our inductor, which is in parallel with a 10 ohm resistor. And we should remember that components connected in parallel have got the same potential difference. Okay, so which means that the potential difference across the parallel section is the same. And because we have got current flowing in that circuit of 0.5, it means that we can find the potential difference across the 20 ohm resistor. When we get the potential difference across the 20 ohm resistor, we can then subtract it from the supply, which is 12 volts. And what remains then is across the parallel section. Are you okay with that?
Yes, sir.
Right. So, which means that to obtain our voltage across the inductor, that will be our potential of our EMF of 12 volts minus the potential difference across the 20 ohm resistor, which is your I R subscript 20. Okay, so VL will be equals to 12 minus our I, which is 0.5 times the 20 ohm resistor. The value is 20, so which gives you 10. So the voltage across the inductor will basically be 12 minus 10, which is 2 volts. So which means that you can now find your di over dt. Di over dt will now be equal to voltage across the inductor over the inductance, and this will be 2 volts over the inductance, which is 10 to the negative 3. Okay, so if you compute that, you can determine what's the value. 2 divided by 10 times 10 to the power of negative 3. So you get 200 amp per second. So that's your rate of flow of current. Okay, that's basically your charge, right? Di over dt. So that's how you would go about that question. So it's almost similar with the expression that we had in the first question, which is question 8. Now let's look at question 10. Do we have an option there? Yes. What does question 10 says? Question says, consider a current in a 90 millihenry inductor changes with time as I equal to 1 t squared minus 6t, where I is in amps and t is in seconds. What is the magnitude of the induced EMF at t is equals to 1 second? Right, so to determine the magnitude of the induced EMF, remember, we said E is equals to negative L di over dt. So which means that this expression will then be d, differentiate that over dt. And if you do that simple differentiation, you'll get that this will be 2t minus 6. So this will be your expression for the EMF induced for the times shown there. Okay, so if you do for the first case, which means for t equals to 1 second, which means where there is t, you substitute 1 second, your EMF will be equals to negative. Your inductance were given, that's 90 times 10 to the negative 3. That will be 1, 6. So basically that will be 2 minus 6, that's 4, which is 90 times 4 should give you 300 and not 300, 90 times 4 should be, let's see, 90 times should be 360, right? So it should be 360 times 10 to the negative 3 volts. So let's see if we've got that option there. Okay, it's in milli, so that will be 360 millivolts already, just to the power of 3. So that will be the option. I'm not going to do the t equals to 4 seconds because basically now you just substitute in place of t, substitute 4. You will try that on your own, right? So what's important is to realize that expression has to be differentiated so that you're given I and you have to determine the rate of change, okay, for the EMF to be induced. So basically that's what you have to do. So we'll check at what time is the EMF 0. So I'll do the last part. At what time is the EMF 0? So again, our expression, we got E equals to negative L to T minus 6 for E equals to a 0. So for E equals to 0, substitute a 0 there, and you remain with negative 90 times 10 to the negative 3. This will be 2t minus 6, okay? And you can divide both sides by 90 times 10 to the negative 3. So that will be 0 over 90 times 10 to the negative 3. And you remain with 2t minus 6, right? So which means that you have your 2t minus 6 equals to a 0. Then your 2t will be equals to positive 6. And if you divide that by 2, you'll get that your t is equals to 3 seconds. So meaning that your EMF will be 0 at 3 seconds or after 3 seconds. Okay. Then you can check. If we've got 3 seconds there. So obviously t is equals to 4. I'm not going to select an answer, so it will come out as please answer all the parts of the question. So you answer all the parts of the question, and then you confirm if these answers are correct. But basically that is the concept. I've left that part for substituting 4 seconds for you to try out and see if you get the question correct. So yes.
So I got, for the 4 seconds, I got 180 millivolts.
180 millivolts. So we can choose that and see if we get all the 3 correct. Okay. All right. So that's correct. That's correct. Thank you for following. So that would be our options. I'll scroll down to show question. Question 11, right? Is it visible? Yes. So the question reads, when a switch is closed, completing an LR series circuit, the time needed for the current to reach 3/4 its maximum value is dash time constants. So when a current is when a switch is closed, which means that the current is going to be increasing, right? The instant when current is increasing, or when the circuit is completed, the current will increase exponentially. Okay. The current will increase exponentially. So the expression, you must have come across it in class for an exponential increase. You have got your I equals to the I max, right? 1 minus epsilon negative RT over L. Do you remember the expression?
Yes, sir, I do.
So this is your exponential. And later on we'll talk about the exponential decrease. So now at the instant the circuit is closed, we expect an exponential increase. So it says what's the time needed for the current to reach 3/4 its maximum value. So which means we want the current to reach 3/4, 0.75 of I max will be equals to your I max 1 minus exponential negative RT over L. So this will be our equation. And once you've done this, then our question is already half solved, because we're now going to cancel out this, cancel out that. We remain with 0.75 equals to 1 minus exponential negative RT over L. Okay. But remember that your time constant is equals to L over R, which means we can factor in our time constant. And the reason why we're factoring the time constant is because our question is asking how many times or how much time is needed for the current to reach its maximum value. How many time constants, right? How many time constants are needed for the time to reach 3/4 its value. So which means we can express it that way. Then this would be 1 minus exponential negative. So which means R over L will be equals to 1 over lambda. So which means that this will be essentially T over lambda. Okay, so now we remain, if we rearrange this expression, you would now have your 1 minus 0.75 equals to, if you take this to the other side, it becomes positive, that's e to the negative t over the time constant. So this would be 0.25. That's e to the negative that's e to the negative t over the time constant. Then after that, what then do we do? After that, what then do we do? We can remove the exponential. We can remove the exponential. So removing the exponential by introducing ln on both sides. I hope your maths is good. It will give us ln 0.25. So we want to determine the time. We want to determine the time. So which means that our time t will be equals to ln 0.25 multiplied by the time constant. So this would be negative, because we've taken the negative to the other side. So we can find what is ln 0.25. So we get negative, and with that negative, then our t becomes positive. So it becomes 1.39 time constants, which means we need 1.39 time constants for the current to reach 3/4 its maximum value. I hope you managed to follow out this one. This was question 11. Are you still following?
Can you please repeat some? I didn't hear some parts of it. I did not understand quite a bit.
Okay, all right. I'll start off from where I put the equation. So basically, we are saying that for an inductance resistance circuit, when the circuit is completed, we expect an exponential increase in the current. The moment you close the switch, you expect the current to increase exponentially. And this is our equation which governs the exponential increase, where I is where I naught, the one that I've now put is I naught, will be the current at this particular time. So we are saying now, or they are saying, find the time at which the current I naught will be 3/4 of the maximum possible current. So which means they're saying find the time at which I naught is equals to 3/4 of I maximum, which is what we've done on equation number 2 there. We've substituted I naught with the 0.75, which is 3/4 of the maximum current. Then we cancel out the maximum current on both sides. We remain with 0.75, and this becomes our equation 3. Equation 3 is now just simple mathematics. It's now 1 minus 0.75, or before we go there, you see from this expression that we have here, we have not factored out the time constant, and the time constant is equals to inductance over the resistance, which means that resistance over inductance is equals to the inverse, which is 1 over the time constant. Why did I do that? Because you can see the expression that I have here, it's resistance over inductance. So in place of a resistance over inductance on this point of the equation, I have substituted for that, and that would give us this expression that we have here on equation number 4. So there we now subtract 1 minus 0.75, you get 0.25. We're now here on equation 5. And to remove an exponential, we have to add ln on both sides. Okay? And ln of this will give you equation 6, which is negative t over tau, which is the time constant. Then from there, you make t the subject. That's equation 7. And then equation 8, you're now basically punching ln 0.25. If you punch ln 0.25, you get 1.39. So which means that the time needed would be 1.39 times the time constant, or 1.39 times the time constant. The time constant is not given in this equation because we don't have the value for the resistance. We don't have the value for the inductance, or for the inductor.
Okay, sir. Now I understand. Thank you.
All right. Okay, so this was question 11. Now let's look at question 12. Just going to scroll down. So I want you to try out this one. Try out this one, read it through, and let me know what value you get. Shouldn't take you more than 3 minutes. So it says a circuit contains two inductors, 6 millihenry in parallel, placed in series with an inductor of 8 millihenry. After one of the 6 millihenry inductors burns out, the repairman wants to replace all the 3 inductors. Which one with one inductor of equivalent inductance, assuming the inductors combine in series and parallel the same way resistors do, what inductance should the repairman use? Please try out this one and let me know what value you get.
Sir,
Yes,
I think I got A,
you got
but I'm not
A.
sure.
What does A say?
3.4
millihenry. Okay.
yes.
All right. Also, I'm not sure what the answer is, but let's try it out together and let's see how you've done it. So we are told that we have got two coils of the same magnitude connected in parallel, 6 millihenry, 6 millihenry, and the other one is 8 millihenry. And the last statement says, assuming inductors combine in series and parallel are the same way resistors do. So, which means that for the parallel section, it will be 1 over L, which is 1 over L1 plus 1 over L2. So 1 over L will be 1 over 6 plus 1 over 6. And that's 1 over L. If you have a common denominator there, that will be 1 plus 1. So that will be 2 over 6. 2 over 6 is equals to 1 over L. So if 2 over 6 is 1 over L, which means L is going to be, so basically this is 1 over 3. So which means L will be equals to 3 millihenry. Do you agree?
Yes, I agree.
Which means that if we have got this, then our circuit simplifies to 3 millihenry, 8 millihenry. And then to get the total there, it will be your L1 plus L2. So that will be 3 plus 8, which should be 11 millihenry. So I think it's B. I think it's B. How did you work out yours? How did you get 3.4? Or you treated this 6 in parallel as in series, then you went the other way. How did you go about that one?
I got 3 over, on the first one I got 3.4 because it was 1 over 8. Then it's gonna be 4, it's gonna be 7 over 24, then it's gonna be 3.4, then 3.4 plus 6, which is 9.4. So yeah, yes.
And
I messed up for the on the first step because I didn't say it's 1 over 6, 1 over 6. I thought it's 1 over 8, 1 over 6 ish. Now I see.
oh, okay. So you missed it on the statement itself. Okay.
Yes,
Yeah. So the method was okay, but you missed it on the statement.
yes.
So it says it contains two inductors of 6 millihenry
Yes.
in parallel. So the
Oh yeah, I didn't
two 6
do
milli
that.
in parallel. Yeah.
That-
Yeah.
Okay, so
Yeah. So yeah. But anyway, at least it's not in a test or TAT. So next time you know you can't miss that.
yes, sir.
Question 13. Consider the pulse IT shown. I'll show it. the current begins at 0, becomes 10 amps between t is equal to 0 and t equals to 200 microseconds, and then is 0 once again, and the pulse is applied to the input of a partial circuit shown. I'll show it. What is the current in the inductor as a function of time for a time t greater or equal to 200 microseconds? Hint, apply Kirchhoff's loop rule. So I'll just scroll down a bit so you could see the circuit. This is how the circuit looks like. So first we have got a loop. I'm going to need this to rotate. Okay. So I was saying first we've got on diagram A the pulse. There is the pulse at time t is equal to 0. It's at 0, and then after some then it rises to 10 until 200 microseconds, then it goes to 0. So that pulse is then fed into that partial circuit, which has got a 100 ohm resistor in parallel with a 10 millihenry inductor. So I'm just going to represent that circuit here. So here we've got 100 ohms, and we've got 10 millihenry, and then we've got our current I, which is flowing at this point. Then obviously we know that we've been given a hint, which means that current is going to split at a junction, right? Flow in this direction. So this would be your current I through the resistor, and we'll have another current here, I through the inductor. You agree? Which means if you are to form an equation, it means that your current I is equals to the I through the resistor plus the I through the inductor. You have to form an equation, right? So the question is asking us to determine what happens at t greater or equal to 200 microseconds. That's what the question is asking for. But for learning purposes, I'll choose, not only for learning purposes, but in order for you to get to t greater or equal to 200 microseconds, you need to start by understanding what is happening at t less than or equal to 0, at t greater than 0, less than 200, and then you can go to 200, greater than 200. So take it in those steps and see how we arrive at t greater or equal to 200 microseconds. So first and foremost, before we go any further, I would say for t less than or equal to 0, what will be the current in the inductor? Just as a starter, what will be the current in the inductor at t is less than 0? If you look at your pulse there,
I think it is also 0, sir.
it will be 0, which means that there's no current in the inductor at that time. So we are not concerned about t equals to less than or equals to 0, which means we will start our analysis for t greater than or equal to 0 and less than or equal to 200 microseconds. Okay, so this is where we have got this equation that we formed, okay, from Kirchhoff loop rule. Now we can then apply Kirchhoff's loop rule, looking at the loop that we have here. Looking at the loop that we have here, and if we consider to loop in a counterclockwise direction. So if we consider to move in a counterclockwise direction like that, it means that now when following in the direction of current, or when following in the direction of current, our potential drop is negative, but when moving in the direction of or when opposing the direction of current, then it's negative. So considering that, we know the loop rule, you've got, that would be your negative I R times your resistor R plus your potential drop across the inductor, which will be L di of the inductor over dt equals to 0. So we are saying that as the current is flowing through the inductor, we're going to have a potential drop across the inductor, and as current flows through the resistor, we'll have a potential drop across the resistor. And another thing, if you look at that connection, components connected in parallel have got the same potential difference. So if you take negative IR to the other side, you will realize that the potential drop across the 10 millihenry and the 100 ohm are equal from this equation that we've just put here. Okay. So one other thing to consider from, I'll label this as equation 2, and this is equation 1. From equation 1, we want to eliminate this IR. From equation 1, IR is equals to I minus the current through the inductor, which means from this expression, in place of IR, we can put that I minus IL. So that becomes equation 3, negative I minus IL multiplied by R plus L di L over dt equals to 0. Okay. So now once we've done this, we can then collect like terms and we can integrate, because remember, there is a change that is taking place. So we can collect like terms. We can have your di over dt on the other side, or take dt to the other side. So we can have like this. L di over dt equals to, now that becomes positive, that's I minus IL multiplied by R. Okay, so if you rearrange this, that becomes your di over I minus IL, okay, which is equals to R over L over dt. Then you can integrate both sides, okay? And for a time, it's varying from a time of 0 to a time t. And for your current, it's varying from a 0 to a current I, okay? Now, if you integrate, so this question is quite long. Feel free to stop me at any step that we're working and ask me to repeat. So I'll just label this as equation 4. So if we integrate that, we'll obviously get ln, so that will be negative, ln of I IL over I, the constant, okay, just current through the inductor. Just need to make sure that I've done the correct substitution. Just checking my steps. So this is our initial current, in case you're wondering which the dot I is. It's not inductor, it's I for initial current. I've been leaving it out, initial current. Okay, so once we're there, then we're good. Integrate dt, you'll get t. So that's where you get your RT over L. So now once you've done that, then you can, again, like we did in the other previous question, introduce, eliminate, in this case, eliminate ln by adding an exponential, right? So you can then take this negative from there and put it on the other side there. And if you put an exponent on both sides, then you'll remain with over current through the inductor over, which is equals to exponential negative RT over L. So this will give us the case for an exponential increase. So it's almost like a derivation of the equation that we used earlier on for the exponential increase. So this is where it's coming from, okay? So this becomes I initial minus IL, which is equals to I naught exponential negative RT over L, okay? So if you do that, then you can collect like terms. So IL of the inductor, if you take it to the other side, becomes positive. Then it becomes I minus I exponential negative RT over L. So which means that the current through the inductor would be equals to, if you factor out that I becomes 1 minus exponential negative RT over L. So this is where the equation for the exponential increase comes from. Exponential increase. I'm sure you remember it. We used it earlier on, right? So from this equation, we can confirm if this is our the expression for determining the current through the inductor, then we can say for t is equals to 0. If you substitute 0 in place of t there, so which means your I through the inductor would be equals to I naught 1 minus e to the power of 0. And e to the power of 0 will give you 1. You can check from your calculator. Then 1 minus 1 will give you 0, which means indeed for t is equals to 0, our current through the inductor will be equals to 0. Okay, so we've looked at for t less than 0, inductor is 0. For t equal to 0, our current through the inductor will be still 0. So which means that our current through the inductor, or we'll start to have a current flowing through the conductor or inductor after t equals to 0. So this was for t equals to 0. Now, how about for this case now? So the expression that we have here, I'm just going to write it down. I've already shown it earlier. Our expression is equals to I equals to 1 minus exponential negative t over tau. That's for exponential because remember we said tau is equals to L over R. So if I substitute that, that's how it becomes. So which means that for time t greater than 0 but less than 200, what is our, sorry, there's no equal sign there, so this is so if you look at the pulse, the I initial is 10 amps, so you can substitute your 10 amps there. So that becomes 10, then this becomes 1 minus e exponential negative t over the time constant. T over the time constant. But what is our time constant? Our time constant is equals to this case. This time we're given the values. So the inductance is 10 times 10 to the negative 3 all over 100. So I can punch that, see what I get. 10 times 10 to the power of negative 3. No, that's not what I want. No, that's not what I want. That's answer divided by 100. That's 1 times 10 to the power of 4. So t is equals to 1 times 10 to the negative 4, which means that 1 over tau will be equals to 1 times 10 to the power of 4, the inverse. Okay. So this is 1 times 10 to the negative 4. If we simplify this, that becomes 10, 1 minus exponential negative. The inverse of that would be 10,000, 10 to the power 4 t. And this is for t less than equals to 0, less than equals to 200 microseconds. Are you following the concept so far? Perhaps I should ask.
Yes, I'm still following.
Okay. So remember, this is not what the question has asked for, but we're just going in stages just for you to have a feel.
Yes,
You never know. Perhaps in one of the questions you'll be asked for from 0 0 to 200, but this one is asking for more than 200. But anyway, we still need to know all of this.
Yes.
So from the information that we've been given, now we can find for t equal to 200 microseconds. So for t equals to 200 microseconds, what will be our I through the inductor? It will be, we're taking the very same equation, put our 10, and that's 1 minus exponential negative your 10,000 multiplied by 200 times 10 to the negative 3. Okay. And then we punch that. So yeah, we can punch that. So that becomes 10. Or let me just do it in steps rather. Exponential of negative 10,000 times, no, what? Times 200 times 10 to the power of negative 3. We get, did I do this correctly? No, I don't think so. What am I missing? Exponential negative. Well, let me just do this. 200 times. Oh, it's micro. I'm putting mil instead of. You missed that as well. That's 200 micro. That's negative 6. No wonder. So 200 times 10 to the power of negative 6 times 10,000 get 2, which means this expression reduces to 10, 1 minus exponential negative 2. So now we can do this, put our bracket, 1 minus exponential to the power of negative 2, 8.65. So which means that our current through the inductor at 200 microseconds is 8.65 amps. That's our current at exactly 200 microseconds. But again, this is not what we were being asked. Now we move on to the actual part which were asked. So now we are considering after 200 microseconds, what happens? After 200 microseconds, what happens? The current begins to decrease. As you can see, it's decreasing until it gets to 0. Okay, so you can say after 200 microseconds, current decays. Okay, then we consider again the loop rule which we had earlier on, and the loop is still the same, so nothing has changed. So it still be negative I through the resistor times R plus d LDI over dt equals to 0. But if you look at your pulse now, if you look at your pulse, after 200 microseconds, what is the current after 200 microseconds on the pulse diagram A?
It's 0, sir.
It's 0, which means that from the equation that we had earlier on, remember we had said I is equals to IR plus IL. Okay, but now this is now equal to a 0 because the pulse is now 0. Okay, the incident current is now 0. All right, so what does that mean? It means that IR will be equals to negative the inductor current. And considering this equation, we can substitute again for IR and we put negative IL in this case. So which means our equation becomes positive at that point. That becomes ILR plus LDI over dt equals to 0. Okay, we do the exactly same thing that we did earlier on by integrating. Okay, so that becomes your LDI over dt equals to negative ILR. Okay, and then you group the like terms again, and you have your integral of di through the inductor over the inductor current through the inductor equals to the integral, which is R over L to T, and your current is varying. Okay, now your current is no longer varying from 0 because you are now already at 200. Okay, going to a time t because our question is saying at t greater or equal to 200. Okay, so we're starting from 200 going to an unknown time. Then here we're starting with your current I to an current that we will determine. So which means that if you integrate that, you'll get your ln of current L over I. Okay, so because it's the upper limit minus lower limit, I'm sure your integration is okay. And then from there, if you integrate that, what do you get? So I forgot to carry over the negative, so you still have your negative there. If you integrate, you get RT over L. Okay, and you have got your upper limit and your lower limit varying from T to 200. So I'm just putting 200. Okay, let me just put the units microseconds. And those are your limits. The upper limit is T unknown minus the lower limit, which is, so you can simply factoring out what is common there. So now what do you do? Then from there, you can now look at your equation. You can remove the ln, put an exponential, right? So after you've done that, or before you do that rather, you can make L the subject, and this becomes Li R No. We can't separate that before introducing len. That'll be terrible mathematics. So to separate this, we introduce len. I introduce exponential. That will be inductor L over I, which is equals to e to the power of negative RT over L multiplied by T minus 200 microseconds. Then you can take the initial current that side, which is I, L equals to initial current multiplied by E negative RT over L bracket T minus 200 microseconds. Right, so this is now our equation which governs whatever happens beyond 200 microseconds, which is what our question is asking for. Okay, now what is our I naught at our I initial?
It's 10.
Are you sure?
Isn't
At time
at
t equals to, remember we're starting from 200.
Oh, okay.
I'll take you back.
Yeah, it's 8.65. Okay.
So it's 8.65 at because remember, yes, we started from 200, right? Yeah.
Okay, so it's
so which means your I naught is equals to 8.65 amps. Then we can substitute in this equation, which means our current through the inductor will be equal to 8.65 exponential negative. We can change all that to be what? To be t over tau times t minus 200 microseconds, and we can simplify this 8.65 exponential negative 10,000 t am I right? No, this t I think I missed, so this should be like minus 200 microseconds. Yeah, so so I repeated this t here, which was eliminated by putting the time constant, the limits. I wasn't supposed to put the t. We already have the t in the bracket here. Sorry about that. So this should just be R over L. So it was now a repetition. T was factored in the bracket already. So your RT is still there, but now T is in the bracket. So instead of this is what we should have. So it's just I through the inductor, L, which is equals to I exponential negative R over L, and instead of T we've got T minus 200 microseconds, which we have in this equation. And then what we then have to do now is to substitute I naught for the initial for your 8.65, which becomes exponential negative R over L, which is T minus 200 microseconds. And remember that your R over L is the inverse. It is the inverse of your time constant. I just lost my display, just a moment. Just a moment, I try and adjust. So you remember from what we did earlier on this part of the question, our inverse 1 over tau is equals to 10,000. So in place of R over L, we can substitute 10,000, which is 8.65 exponential negative. Anyway, you still have the values for R and L. If you substitute R and L in that place, you get 10,000. We worked it out earlier on. So that becomes 10,000. Look at T minus 200 microseconds. Okay, so essentially you're done. So this is just algebra. So this becomes 200. No longer 200. It becomes 2 actually. It becomes 2. Why? Because we have multiplied 10,000 by T, 10,000 by 200 microseconds. You get your 2. So like this. So remember again your indices. This would be the same as 8.65 exponential to the power of 2 times exponential to the power of negative 10,000 t. You combine the exponentials, you add the powers. Okay, so still get the same thing. So now why we did that, so that we can get a numerical value, which will be basically punching times so you get 63.9 amps exponential negative 10,000 t in seconds. So that's how you would find your current. So the important thing there in this question is I just decided to make it long, but you can see that there is no way you would find the current through the inductor at time t greater than 200 microseconds without determining the current or the value of current at 200 microseconds. So even if it was asked for greater than 200 microseconds, you still needed to start from what is happening at 200 microseconds. So it's quite a long question, but I think it's worth practicing to understand the concept. I'm not sure if you are happy with that.
Yes, it needs practice so I can understand more.
Yeah. So take time to go through it again. See if you can follow what we've just done. Also try it on your own and see if you're able to follow through. Then the last question is question 14. That will be the last question we'll do today. This one is a short one. So it reads, when the current in the portion of the circuit shown in figure is 202 amps and increases at a rate of 0.5 amp per second, the measured voltage is 9 volts. When the current is 2 amps and decreases at a rate of 0.5 amp per second, the measured voltage is 5 volts. What is the value of what? Of the inductor and the value for the resistor. So this is how our question looks like. So it's just an impartial circuit. We're expected to find the value for the inductor and the value for the resistor there. So first and foremost, we'll obviously have to start with looking at the quantities that we are given. So we're told that for a potential of 9 volts, we've got an increasing current. So I, for the first case, I is equals to 2 amps, and your di dt is equal to 0.5 amp per second. And when the current is increasing, okay, when the current is 200 amps, okay, so here for the first case, delta VA B is equals to 9 volts. Then for the second case, again, current is equals to 2 amps, and your di over dt is equals to 0.5 amp per second. And our change in potential VAB is 5 volts. All right, so then what do we do? So looking at our circuit diagram there, to find the potential VAB, it will the potential across a VAB is basically the sum of the potential drop across the inductor and across the resistor. So which means that essentially VAB is equals to voltage across the inductor plus our voltage across across the resistor, or in any direction if you like. So which means that VAB will be equals to your the current I R plus your L dI over dt. So this is the very most important thing on this question, to realize that the potential difference across VAB is the sum of the potential drop across the inductor and the potential drop across the resistor. And this applies in both cases. However, it will determine or depend on what is happening. So the first case, what are they saying? So if you notice the first case, when the current increases at a rate, so which means di dt is increasing for the first case. Okay, it's increasing. Then for the second case, di dt is reducing. So that has got an implication. So let's consider equation 1 for the first case. VAB is 9 volts and our current is 0.5 and our resistor is unknown, so that becomes 0.5 R plus the value for our inductor, which is unknown, and our current is not 0.5, it's 2 actually. It's 2. So I've simply substituted into this equation. Then equation 2, I do the same. I substitute 5. It's 2R. Now it's negative because the rate is reducing. So that becomes negative L times 0.5. So to simplify, now you have formed a simultaneous equation. So this can solve simultaneously. So I can see you can easily eliminate your R there by saying equation 1 minus equation 2, which becomes 9 minus 5, which is equals to 2R minus 2R minus then plus 0.5 L plus 0. Yeah, it becomes plus, so it's okay. Let me just put it explicitly in case someone wonders. So that's 0.5 minus 0.5 L. So that becomes 4 equals to L. So which means your inductance is equals to 4 Henry. Then because the simultaneous equation, now you can pick any equation. 5 equals to 2R minus 0.5 L. So that's 5 plus 0.5 L equals to 2R. Then that becomes 5 plus 0.5 times 4, which is equals to R over 2. So that becomes 5 plus 2 over 2, which is equals to R, and that means R is equals to 3.5 ohms. So your resistance is 3.5 ohms. We can check this. Okay, my screen disappeared, but we were already done. Inductor 4 and resistance 3.5. So we can check that. So yeah, so it means we are correct. So that is basically how we would go about that particular type of a question. I'm not sure if you managed to learn something from today's tutorial. Did you learn something from today's tutorial?
Oh, yes, sir, I did learn a lot. Thank you so much.
You're welcome. Are you in the PHYV group?
Yes, sir.
Okay, so I hope that this will add to the preparation of your test. I'm sure you are busy with preparing for it. I hope so.
Yes, sir. It will help me a lot. It will add
Yes,
something.
yes, I'm sure it will. So this is what I had for this afternoon. Be sure to join in again tomorrow. There'll be the last tutorial before the test, just to make sure you get practice. So, and all the best for the test.
Okay, sir. Thank you so much.
Yeah, welcome.